Okay, folks, let's see, let's get this going here. Okay, so we are doing law of cosines. We're going to get a start on this. This is going to take us got a couple of days allotted for that. The law of cosines, very, very handy thing to do here. Okay, so I brought some of my super friends here of both math and physics, Albert Einstein, Mukau, and Motormouth. They're going to they're going to keep us company while we get going in here, and I might ask them some questions. We'll see how I do on that. All right, now law of cosines. This is a relationship between sides of a triangle and angles in a triangle in general. And so what I'm going to try to make a point at right off the bat is that it takes the idea of Pythagorean theorem and it extends it. It makes it more general, so it's not just right triangles with right triangles, you can use the Pythagorean theorem. But if it's not a right triangle, you can't use the Pythagorean theorem. However, law of cosines is a more generalized version of that, a more broadly applicable one. All right, so let's get it going here. All right, so I'm going to draw some random triangle that is going to have a corner A, a corner B, and a corner C. Okay, that is a B up there. So there's an angle A, an angle B, and an angle C. And then it is standard for us to say, okay, then the various sides, if you go opposite the angle, we tend to call that a lowercase a. That's the length of this side, and then a B, and then a C, like that. All right, now here is one of the things in 6.5. We saw the following. We learned, all right, that the following is the case, that the law of sines can't solve the triangle. Phrase it like that, so it can't solve the triangle. Remember, idea of solving the triangle is that you figure everything out, basically get all sides, all angles in there. And the law of sines, nice and simple one, very powerful, has two shortcomings in it. Um, it is problematic for if you have the following: side angle side or side side side. All right. Now these were cases 3 and 4 in that particular section in there. So go back and you look at that in the section on law of sines, you will see that those are two places where it doesn't work. But hey, they're down. So there's red. Oh, that means stop. No, let's go. Let's go green. All right. Law of cosines saves the day, comes to the rescue, whatever you want to call it in there. All right. So let me just cut to the chase here. I am gonna show you how law of cosines actually why it works the way that it does. That'll give us a chance to actually do a little practice on that, a little practice with our various trig functions in there. But let me first just cut to the chase and tell you there are three relationships. Any triangle. I didn't say what their length, what their angles were. I didn't say does have any obtuse angles. Did I say? Didn't say. Are they? Is it a right triangle? Is it not? It is any triangle. And in general, the relationship between the three sides and an angle will be given to look like this. So far, that should be looking kind of Pythagorean theorem-ish. And all right, so side A relates to side B and C and its own angle by a formula that looks like a Pythagorean theorem, b squared plus c squared minus 2bc cosine A. This is the new part. We're going to see where that comes from. But this works for any of the sides. So b squared, but don't be too squared because then people will think you're a nerd. Will look like this. So notice this side that is related to the other two sides, Pythagorean theorem-ish, Pythagorean theorem-like, and then, but the other two sides and its own angle, B. So it's actually the same formula, just saying, okay, let's do it instead of for side A, let's do it for side B. And then, if you are seeing the pattern, I encourage you to see the pattern. It's going to look like this for side C. So notice you got the other two sides, Pythagorean theorem like, then this extra trig term in there that takes into account. This is what compensates for the fact that, oh, this is no longer, we're not specifying that this is a right triangle. All right, so first thing to notice, and I've been claiming this is a more general version of the Pythagorean theorem. We are taking that same idea, trying to relate the various sides of the triangle. The only difference is that in a right triangle, you already know one of the angles. That's some hidden information that sometimes we forget that we actually know that in there. All right, so now if we have a right triangle, so if we are dealing with our classic right triangle, we actually already know what that angle is. I'll use C as that. I'll say that if we got a right triangle, if this angle right here were a right angle, then angle C would be 90 degrees. And so angle C here, and side C is then the hypotenuse of that triangle. All right, so let's see, does this indeed work? All right, well, it better. All right, so, okay, so if C is equal to 90, if angle C is equal to 90, one of the things that's going to come out of this is that if you think, all right, well, that means then it is the case that if I take cosine of C, so I'm actually focusing on this one down here, the third one. All three are equivalent. I'm just got to choose one to make your example. So I'm going, all right, then cosine of C is equal to cosine of 90. And hopefully we're getting more and more comfortable with the idea that cosine of 90 is actually equal to 0. If you think about those x and y coordinates, idea that if you've got a 90-degree angle, if angle is equal, theta is equal to 90, x is equal to 0, that x component, that x coordinate part of it in there. All right, so cosine C is equal to 0. Wait a second, but look over here. That means that it will be the case, following logically, that in this special case, C squared equals A squared plus B squared. Now, again, these are the sides of the triangle in there. And so, what do you know? That's Pythagorean theorem, just with the special case that the angle is, there's a 90-degree angle in that triangle. Boom, check, good, we're okay. All right, so let's actually prove this. Let's take a look at this. And the proof is, it's a little bit subtle, but it's not too bad, and it gives us some good practice. So we're going to do two things here. We are going to prove it, and we are going to practice. Right, so we're going to do both of those things. All right, let's move this over here. Get another. Move my notes, and all right. Okay, so let's keep going here. All right, so okay. Now to prove this, I'm going to do it similar in the way your author approaches it. Actually, there are a bunch of different ways that you can do this, all of which are equivalent. But I'm going to put it onto the XY coordinate system. Now, I claimed, okay, if you kind of pay attention to that, you can see a lot of things but I'm going to put it onto a XY coordinate system in there, and I'm going to put the corners of my triangle at various strategic places. The most strategic is I'm going to put that vertex A, that corner of the triangle A. I'm going to put it at the origin. So there's my one part of my triangle. I'm going to go over here, and I'm going to put my corner B over here. And now here's where I want to be tricky, clever, and I'm going to do it the way your author does it. Set it up in there. So now let me first draw the triangle. All right, so if you indulge me, I'm going to turn it a little on the side here. So here is one side of my triangle. Here is another side, and here is yet another side. Okay, now looking at that, here's what one of the things I want to convince you now. When you look opposite of the corner, the angle, so this would be then side A, this would be side C, and this would be side B. Okay. All right. Now looking at that, here's something I can get right away. Here's where B is located. B is located at C0. So it's along the x-axis, a distance C, and it is got no y component to it. So, all right, so that's C is 0. Um, Here's the question I need to ask myself. Here is the key to figuring out why does the law of cosines actually work in there. Okay, so where is C? So I'm going to ask the question, what's the location? In other words, I'm going to say, what are the coordinates of the corner C? So hopefully I didn't squeeze that in there too much. In there, I've got coordinates for A. I strategically put that at the origin. I've got a for B, I put that strategically along the x-axis. So then that along with that side there, C, no, remember that's C, that is the opposite of there. But all right, where this is located is tricky. But it is very, very doable. Very, very figure outable. Okay, so I am going to draw a triangle again. I'm going to take my triangle and I'm going to draw it out here a little bit. So indulge me. All right, so here's my triangle doing something like this. Not so use your imagination. I've got them all set up the same in there where I've got this side is A, this side is B, this side is C, like so. This angle right here is angle A in there. All right. And okay, now here's where I'm going to get, here's where the origin part, I'm going to make this, the origin part's going to come in handy. Okay. Drew dotted lines like this. I am now making a bigger right triangle. All right. So this right here, notice that I've now made it so I have a right triangle and hypotenuse A. Okay. So I'm going to claim that this is that you should see in here a right triangle with hypotenuse that has a length of A. So here's the hypotenuse on a right triangle, like that, okay? Now now if you look at this side over here, this is that Y component for A. That's that Y component right up here, boom, 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 boom. This side is just equal to B sine of angle A. This side right here, that vertical component, that Y component, right? Now, that's this side right here. Now, this little green side here, just the dotted line, remember, this is the origin, just the dotted line is B cosine, right? All right, so now looking at this, all right, that means that I have got this new triangle in here. And all right, so one side of it, I'm going to draw, you guys will indulge me. I now have a right triangle that looks something like this. This side is A, this side is B sine of A. And, oh, by the way, you might see that I didn't have to call this theta. This I should call A, make a correction in there. Didn't have to call that theta. That is just sine of A, cosine of A. That's the x component. Now this side over here, here's where we got to be careful. This side is equal to C minus B cosine of A. Right now, your inner skeptic should be screaming at me and going, Mickey, Mickey, Mick. Actually, a lot of people do call me Mickey. Um, Mick, why is that minus? Why did you put a minus sign in there? Why isn't it this plus this? Here's the key. Why this is minus is that this C is on the positive side of the x-axis or the y-axis. This side, B cosine, is on the other side. They're on opposite sides of the origin, which means that this overall length is actually this side minus that side. Little trickiness in there that we got to keep track of what the sign actually is of that. All right, so that's one of the things that makes the derivation have a little bit of trickiness to it when you're trying to get it set up. All right, so because this is over on the other side of the origin, that is technically a negative number. So to get it to be the overall length distance from here to here, it's C minus there. Okay. So, but once we've got that, pretty good shape. Okay, so now we're going to apply Pythagorean theorem to, we're going to use Pythagorean theorem on our right triangle that we just built using what we know about these various trig functions in there. Okay, so now let's see. All right, got these various sides in here. All right, now, okay, so now I'm going to go and I'm going to take this first version, law of cosines. All of these are applicable. You could use any one of them. I'm going to go to the first one because what I'm actually trying to figure out in here is I am trying to make a relationship between A, B, and C, and I just want to see if I can prove it for one of them. It's proof for all of them. So let me go to the first one. Let's think about that. All right, so we're going to go Pythagorean theorem on this one, and I'm going to see if it does indeed match the first one. It's gonna. Okay. All right, so Pythagorean theorem, hypotenuse squared equals leg of the triangles. Okay, so I'm going to go C minus B cosine of A squared plus B sine of A squared. So that is hypotenuse equals the square of this side plus the square of this side plus equals square of this side plus the square of this side. This is Pythagorean theorem applied to my new right triangle. I am going to see if I can get it to look like that first one, see if it does indeed hold. All right. So let's do a little rearranging and things. Let's use some of our Math 118 tricks. Let's expand this one. I'm going to apply this. I'm going to use FOIL basically on that. So that is going to be C squared. So first, then I want to do outer and inner in here. It's going to be minus 2B times C cosine squared, cosine squared of A. So you did outer, inner. I got two of them in there. That's why I got 2 in there. And then I'm going to square the last one, and that is going to be the minus will square out. And then we'll have B squared cosine squared of A, like so. And then over here, when I square this, everybody inside gets squared. This one a little bit easier. And it'll look like that. All right, now you might look at that and say, oh, what a jumbled mess. What do I do with that? Here's something you always want to look for. When you start seeing sines and cosines like this, there's a particular identity that we've seen. It's in it's in the various chapters in the text. It's one that we are going to try to get more and more comfortable with. We've seen it, but let's remind ourselves that in general, all right, you start seeing these, start thinking about trying to put the sines and cosines together. So I'm going to do one more step, and then I'm going to apply that identity. All right, so I'm going to have this. I got C squared minus 2BC cos squared A. I'm going to combine these two. Notice these both have a b squared. I am going to pull the b squared out in front, and it's going to look like this. All right, so see how I factored the b squared out here? So notice I'm actually, what I'm doing is I'm getting these to combine. So I'm going to pull those ones out like so. All right, and okay, so I've got a squared is equal to this. Now here is the crucial thing. Here's an identity. This is always true. Um, Sine squared theta plus cosine squared of theta is always equal to 1. If you add the square of the sine and the cosine, you always get 1. It's the same angle. That just works. It's actually Pythagorean theorem for a triangle of a hypotenuse 1. All right, so that means that we can go like this. All right, so we can go a squared is equal to c squared minus 2bc cosine squared a dot there. All right, this is just plus b squared. All right, I'm going to do a little more uh, rearranging on this, but I'm not going to have to do much more on this one because I have a squared is now going to be equal to b squared plus c squared minus 2 times b times c, all of that, times 2, and all right, times cos. Oh, and by the way, okay, folks, I want you to notice something in here. Did not need the squared here. So go back, fix that, because I took a look at it and said, oh, wait a second, that doesn't quite work. In there, yeah. When we multiply it together, we get the b and the c times cosine. So it did not need the squared there. This one does get the squared. All right, and so then this is going to be cosine of a. And if we take a look right here, all right, there it is. All right there. I'll get that there, right there. All right, a squared, b squared plus c squared minus 2bc cos a. Just remember, did not need that squared in there. Don't let that transcribe into your notes. All right, so let's see. Let's keep going. All right, now, what I want to do, I'm going to do a apply law of cosines. Like I said, let's do some practicing in here. And this one, okay, this one near and dear to my heart. So I took one of the problems. This is from your section 6.6, and it's a word problem. It's actually not too bad, but basically you got a car traveling along a straight road, heading east for an hour, then traveling half an hour, leads northeast in there. All right, and so then, and going at 40 miles per hour. All right, so this is what the car is doing. So if you take a look at this, if you think about what's happening, the car is going to travel. It's going to go, all right. So it's going to go 40 miles in the east direction. So if you think in terms of a coordinate system, we're going to travel this way 40 miles. Then we're going to travel northeast. So we're heading east, then we're going to go northeast. Now, what's crucial there is that is going to be 45 degrees right there. And this side of the triangle will be 20. So it makes a triangle like this that has a side of 40, a side of 20, and then there's an angle 45. Looks like this. Okay. Now, looking at this, here's one of the things I want you to convince yourself of. That means that this angle right here is equal to 135 degrees. Okay, so make sure that this looks okay to you. You look at this and you go, all right, okay, 40 miles this way, we go 20 miles this way at a 45-degree angle. So going east, going northeast. And then that means that, oh, okay, so then if we draw, then this is our overall distance from here. Here's where we started. Here's where we ended in there. So the question is, well, how far did we actually go in there? So I'm going to put a variable x right here. All right, so notice what we've got. We've got side angle side in there. So this is actually a side angle side problem in disguise in there. All right. And so now looking at this, all right, I am going to go and I am going to apply law of cosines to this. All right, so let's take a look at this. I am going to claim that the following is the case. Here, x squared. Right, so notice in the law of cosines, we are always putting one of the sides in there squared. Then it is equal to the sum of the other two sides. All right, so I'm going to go in here and say, all right, I've got 20 squared. That's one of the sides. I've got 40 squared. That is the other side. Then minus 2 times the product of those two sides, 2 times 20, 2 times 40, and then cosine of the angle that is opposite of the side that is out here on the left. So this would then be cosine of 135, like so. Okay, now take a look at that. Now the tricky part is I threw a little physics problem in there, where you had to go and say, well, what is this distance 40? What is this distance 20? Where are those angles? Through a little bit of application in there, but good problem. Now taking a look at that, notice it's really plug and chug because x is just going to be square root all of that stuff in there. Right now, one thing that's important in there, I've got an obtuse angle here, so that's going to affect the sign of the sine, the sign plus or minus, not the sinusoidal. Um, this cosine in there, so you got to be a little bit careful with your pluses and minuses in there. But just take that whole thing and take the square root of it. So I took square root of both sides, and when I do that, I just end up with x punched into my calculator. I get something that is around 56.0. And by the way, that will be miles because this is 40 miles. This is actually 40 miles. And this side is 20 miles, like that. So kind of nifty application of law of cosines in there. All right, let's keep going. Okay, so let's see. All right. All right, so that was we're gonna do, let's see how we do. Let's do another side angle side. That was a side angle side in disguise in there. So let's do another side angle side. Let's do another side angle side. So let's set it up like this. So again, it's gonna be a random triangle, some triangle. Call this A, call this B, call this C, like so. All right. And so over here, I'm going to be given the following. That C is equal to 18, B is equal to 10, okay? And then A is not going to be known, but we are going to put a little question mark in there. We don't know what side A is, and we are going to know that this side of this angle over here is 40 degrees. Okay. And so let's solve the triangle. Now, I'm going to end up using law of cosines and I'm going to use law of sines on this one. All right. So first thing that I'm going to do is I'm going to abbreviate this LOC, law of cosines. And I'm going to use that to get a calculation for that side A. We just did a side angle side. threw a little bit of a curveball in that we had to figure out what the distances were first. But all right, so but now looking at this, I've got this side, I've got this side, I've got this angle. I can get that final side because I am going to go right back to law of cosines. Oops, this is equals. So b squared plus c squared minus 2b cosine 2bc times cosine of A. All right, there we go. All right, this is actually plug and chug. Wait a second. I know these two sides. I know this angle. Oh, all right. A squared is equal to 10 squared plus 18 squared minus 2 times 10 times 18 times cosine of 40 degrees. All right. Convince yourself this is plug and chug. All right. So now when I calculate this, so plug all of that in, square root of that entire thing, and I end up getting a being approximately equal to 12.17. Do notice that in this problem, I didn't actually put any units in there. In the previous problem, we were talking about miles, so we did actually keep units in here. A lot of times in these more kind of abstract theoretical problems, we don't necessarily specify when we're just practicing our trigonometry. We don't say, are we dealing with miles or feet or inches or something like that. All right, so law of cosines. We had side angle side. That got us our third side. Now, for solving the triangle, we'd like to get the other angles. And so here is what I'm going to do. That is, all right. Now what I'm going to do is I'm going to use the law of sines. Indulge me, law of sines, less like so. And I'm going to do that to find the value of angle B. So we've got all three sides. Now I can actually go to law of sines. So if you go back, I'm going to basically remind myself in the law of sines that the relationship between the sines of the angles and the sides opposite of those angles, that law of sines says that sine of angle A over side A should be equal to sine of angle B over side B. And if I take a look at this and I do a little rearranging on this, then I get that sine of angle B. Okay, so I'm looking for angle B is going to be equal to B times sine of A all over A. All I've done is multiplied both sides by B, and I brought that B up to the numerator, that side. That leaves me with sine of B. Now here's where I got to be. Here's where I got to be. Again, a little bit careful. That means that I'm going to take the inverse sine of this. Remember those inverse trigonometric ones. Now your author often writes this as saying that, okay, tries to make it look like certain calculators. My calculator calls the inverse sine to the -1. That can be a little confusing because it might make you think of reciprocal, but it means inverse function. And so inverse sine, be a little bit deliberate there. I'm going to try to use both because depending on what calculator you use in there, yours might have a little inverse sine, INV, like a little abbreviation. You might also have it as a raised to the with a -1 right there. That's what my calculator looks like in there. They're the same thing. It is the inverse sine, not the reciprocal, but the inverse. And so if I take B times sine of A divided by A like this. So in other words, if I do inverse sine of this, and I do 10 times sine of 40 all over around 12.17, although in mine, I actually stored some numbers in there, but I'm going to do it every single time. But right now I'm going to actually say, all right, How do I do this? I'm going to go second function, and I'm going to go to my inverse sine. That's sine to the negative, looks like sine to the negative 1. It's not. It's inverse sine. I'm doing inverse sine of 10 times sine of 40 divided by 12.17. I'm going to close that off, hit enter, and I get around. I did a little bit of rounding off in there. So when I punch it in and I've got this rounded off, I've got 31.88. Will you guys allow me to put, because I put the more exact number in, and I got 31.87. That is a round off difference. I stored the entire number, this one, in my calculator when I did the calculation of 31.87. All right, there we go. We've got angle B. Now that was from using law of sines, and gives us a little practice with those inverse functions in there. And then I want to solve the thing, so solve the entire triangle. Now I could go back to law of sines on this one. I don't have to anymore because I know two of the angles. I've got all three sides. Um, Now that third angle is just going to be, if I take 180 and I subtract off A and I subtract off angle B in there, we should be all right. So C in its angle, this is a degrees, by the way, will be around equal to, I'm going to go 180. Now then minus angle A, which is 40, and then minus B. Again, this can have some round off error in there, and depends on whether you store all your numbers, where you round off, how many digits do you keep. So don't get worried if you're off by a couple of decimal points in there. But when I do my calculation using the number that was stored in the memory in my calculator that keeps all the digits that the calculator can handle in there. All right, so I end up with that angle in there. And what do you know? We have solved the triangle. Law of cosines to get that third side on there. Law of sines to get one of the other angles. Just knowing that a triangle is 180 degrees to get that final one in there. All right, we got one more. We're going to call it for this particular video. Okay, so let's see. All right, now let's do a side, side, side. One of the things that I claimed is that the law of sines, while a very powerful and a very easy to remember formula, it has the shortcoming in that it doesn't it doesn't solve a side, side, side for us. It doesn't help us. Right, Einstein? Correct. All right. Right, Mukau? Right, Motor Mouse? Yes. All right. Kept forgetting to bring those guys in. All right. Okay, here we go. Side, side, side. Let's do an example. All right. So again, I'm going to just take some particular triangle, and I'm going to have A and B and C. Oh, look at that. I'm mixing it up. Now, don't assume anything about the angles. That the way I drew it, that looks like maybe that's a 90-degree angle. Do not trust that. Then over here, I'm going to have B equal to 10. I'm going to have C equal to 20. So notice these are the ones that are opposite that angle in there. And I'm going to have A equal to 12. Okay? And this is not, I made no attempt whatsoever to draw this to scale. So you cannot look at my diagram, look at my drawing here, and make any kind of assumption about, is that really a 90-degree angle? Are these both acute angles? Don't trust that. I didn't actually put a lot of thought into when I drew it. I just put it up there and actually wanted to make a point about that. Okay, we're going to do I'm going to use an approach very similar to what we did in the last one. I am going to use the law of cosines, and I'm going to use that, and I'm going to get angle C from that. Then I'm going to go and I'm going to use the law of sines to get angle B, and then I'm going to subtract from 180 to get angle A. All right, let's go for it. All right, so I got a three-step, very similar to what we did in the previous one, except this is side, 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 not side, angle, side. Okay, so here we go. So I'm going to start with this. C squared equals A squared plus B squared minus 2 times A, B, cosine of C. Okay, so that is just one of the law of cosine identities that we have in there. Again, generalized version of Pythagorean theorem. Except we're letting C not necessarily be 90 degrees. All right, so now I'm going to claim now I have to do a little bit of algebra on this because I'm looking for angle C. That's my first thing. If I get angle C, that gets me going but I've got to figure out are the angles. Well, I mean, what is your angle? Okay, 20 squared equals 12 squared plus 10 squared. All right, you see how I'm plugging in for A and B? Minus 2 times 12 times 10 times cosine of angle C. Now take a look at it. Make the realization that by setting it up like that, I've got one equation, one unknown. My favorite number of equations and unknowns, because I've got all of my numbers in here except for angle C. All right, so but I got to do a little bit of algebra because I've got to isolate the cosine. And then we will find ourselves again doing an inverse in there. So let's go. All right, so 400 is equal to 144. Just squaring these out. Plus 100 minus 2 times 12 times 10. So that is going to be minus 240 cosine of C. Now you are going to have to mind your pluses and minuses in this. So let's go up. I'm gonna isolate the cosine C, and then I'm gonna use my calculator to do my inverse function in there. All right, so now if I do a little rearranging in here, this term right here, I'll have negative 240 times cosine of C. So basically what I'm doing is I'm gonna get all of this stuff over to the other side. I'm gonna subtract 144 and 100, so 244 from each side. That is gonna leave me with a total of 156. The 400 minus 144 minus 100. All right, I'm going to make that the right-hand side of my equation because I want to solve for cos C. But what I'd be left with over here is that negative 240. The negative is important. Do not drop it. On occasion, when I'm working these problems, I get sloppy and I drop the negative sign in there, and then I feel terrible and I get the wrong answer. And I find myself mad at myself for being sloppy and losing track of my negative signs in there. All right, so don't be like me. All right, so you're gonna divide both sides by 240, and that is why I gotta be careful in here, and it's not gonna mess me up. All right, so here's what I'm gonna have. I will have that C is the inverse cosine. So of what is left over here, I am basically going to have negative 156 over 240. I'm not even going to bother calculating that because I can just do that right away on my calculator. Now, looking at this, okay, so I'm going to calculate this. I'm going to get an angle for it. But actually looking at this, if this side is 12 and this side is 10, then it does seem like C should be a large number. Um, a, a, and so let's see what do we actually get for our value in there. All right, so I'm going to do my inverse cosine. So mine, I go second function cos. Now it looks, mine again, makes it look like it's a reciprocal. It's not. Inverse cosine of, and I am just going to go negative 156 divided by 240, like so. And hit enter, and I do indeed get a number that is big. So I get C, actually get something obtuse. 130.54, 6, et cetera, et cetera, et cetera. So we're looking at something around 130.54 degrees. All right, so there we go. I got one of my angles. All right, hey, I did that first part. All right, let's go to law of sines now. So if we go now to law of sines, sine of B over B, so remember the sine of the angle over the side opposite that angle, is always going to be equal to the sine of, now I've got angle C in there, and so sine of B over B, sine of C over C, and which means that I can then do a little bit of rearranging in here, and um, this is saying that sine of B is equal to B times sine of C all over C. And now I'm going to do a very, very similar thing to what we did in the previous problem. And again, I'll write it as inverse sine. I'm going to try to mix that up. And so now, but now what I'm going to end up with is, all right, what have I got? B. So I'm going to, in my calculator, I'm going to plug in 10 times sine of C. I again kept all my digits, but it's going to be somewhere around this sine of 130.54. So B times sine of C all over C. So that is all over 20 like that. And how am I doing? I'm getting low on time in here, so I gotta finish this off. All right, so do the number crunching on this. Since I am getting low on time, we'll cut to the chase on this one. I get something that is around 22.33. This will also be subject to any rounding off that you do, so just be aware of that. Not a big deal, close enough for government work. It depends on what you're doing. You might want it to be really, really precise. Right now, we're just trying to see how the laws of cosine, sine, and work together on that. All right, so I got my two angles. Now I'm going to get my third angle. Very simply, I'm just going to subtract from 180. So I'm just going to go 180 degrees minus 130.54. Let me put a little approximately equal to, and then I'm going to subtract off my last one here. And again, you got to make sure we're dealing with approximate where you round off. Again, I kept a whole bunch of my numbers, and so I ended up with mine being around equal to 27.13 or so. So notice we have 180, so that's going to minus 130. It's going to leave me with about 50. Subtract off another 22, and so I should have something more than 25 in there, and I end up with this. All right. I'm out of time, basically out of time. All right, folks, pause this.